Hello everyone, this is Ketish here. In this video, I'm going to go through the AQA Combined Science Chemistry Paper 1 Foundation Tier from 2020. This paper is 1 hour 15 minutes long and is out of 70 marks. It has a total of 8 questions. Now, in this video, I will be going through questions 1 through 5. All these questions are foundation tier questions, and the last 3 questions are higher tier questions, meaning that question 6 is actually question 1 in the higher tier paper, question 7 is question 2, question 8 is question 3, and question 3 has a 6-mark question. So if you're doing the higher tier paper, you can expect the third question to have the 6-mark question. There's only one 6-mark question which appears in the foundation tier and in the higher tier in combined science. So question number 1 is on the topic of chemical changes. This question is about acids and bases. What is the pH of sulfuric acid? That should be 1. If it has pH of 7, then it's neutral, like water. If it's 14, it's a strong alkali or base, like sodium hydroxide or ammonium hydroxide. An acid reacts with zinc to produce zinc chloride and hydrogen. So here you've got a acid reacting with a metal to produce a salt and water. So acid plus the metal, you got the salt plus, not water, hydrogen. Which acid reacts with zinc to produce zinc chloride? In order to produce zinc chloride, you would need hydrochloric acid because the chloride comes from this part. If you react the zinc plus hydrochloric acid, you will get zinc chloride. If you react it with nitric acid, you would get zinc nitrate. And if you react it with sulfuric acid, you'd get zinc sulfate. What type of substance is zinc chloride? Zinc chloride is a salt. So remember, an alkali is if it has an OH ion. A base is usually a metal oxide. Example is again sodium hydroxide and calcium oxide as examples. An alkali is a base in solution. What compound is an alkali? Which compound is an alkali? Sodium hydroxide. Sodium nitrate and sodium sulfate are both salts. The formula of the copper ion is Cu2+. The formula of the oxide ion is Cu2-. What is the formula of copper oxide? Now, the 2+ and the 2- cancel each other, so you will just have CuO. A student reacts an acid with copper oxide. The reaction between an acid and copper oxides, remember copper oxide is a metal oxide, is very slow at room temperature. How could the student speed up the reaction? Well, if you want to speed up the chemical reaction, one of the easiest way is actually to heat it up. So heat the mixture. You could also, because you're reacting it with an acid, you could increase the concentration of the acid. or use a more concentrated acid. Increase the concentration of acid. That doesn't mean that you're adding more acid, you're actually adding a strong acid. 3. Now, they haven't said this. Copper oxide is actually a solid because it's a base metal oxide. So it's a solid. So would you, if you were using pieces, you could add powdered, add copper oxide. The reason is to increase the surface area, right? To increase surface area. Complete the sentence to show how the student makes sure that all the acids react. The student adds copper oxide to the acid until the copper oxide is in excess. Excess meaning that you've added too much so that it's not actually reacting anymore because all the acid has been neutralized by the copper oxide. The student filters the unreacted copper oxide from the solution. Which apparatus does the student use? You would use this, a plastic funnel and a filter paper. Funnel plus paper because you're trying to filter it. This is the process known as filtration. Now here what you're seeing is an evaporating basin. Why would you use it? This is to basically to carry out crystallization. This is distillation. In order to separate two liquids of different boiling points. This is a distillation setup. It's not fractional distillation, it's just simple distillation. This is chromatography. What process is used to produce copper salts, crystals of salt from a salt solution? That would be crystallization. And that would be this setup. You'd simply add the salt solution into the evaporating basin and heat it using a water bath till you evaporate half the liquid and then leave it to crystallize on its own in a warm place. Question number 2 is on the topic of energy changes. A student investigated a temperature change when metal X was added to copper sulfate solution. This is actually linked to a required practical on energy changes. This is the method used. Add 25 centimeter cube of copper sulfate solution to a beaker. So measure the temperature of the copper sulfate solution. Add 1 gram of metal X and stir. Measure the highest temperature reached when metal X is added to copper sulfate solution. So metal X should actually be reacting with the copper sulfate solution. If it did, then metal X would actually form the metal X sulfate plus copper. Repeat steps 1 to 4 with different metals. Okay. Repeat. Figure 1 shows the apparatus used. You've got a thermometer, copper sulfate solution, metal X in a beaker. Figure shows the thermometer reading of the copper sulfate solution at the start of the investigation. Now there is 21 to 22, there's 10 divisions. So each division is 1. So this is actually 21.1 degrees Celsius. The highest temperature reached when metal X was added to copper sulfate solution was 35.5. Use figure 2. Highest temperature is 35.5. Temperature at the start is 21.1. Let's double check that again. It's 21 and it is up to the first bar. So the temperature change is 35.5 minus 21.1 will give you 14.4 degrees Celsius. Give two variables the student should keep the same in this investigation. So if I look at the setup again, the two things that they would want to keep the same is the volume of copper sulfate solution added, and also adding 1 gram of metal. You're going to change the different metals anyway. So which is going to be my independent variable? So this is my independent variable. These two are control variables, and measuring the temperature is my dependent variable. So two variables that you want to actually keep the same. Mass of metal added. Second one is volume of copper sulfate. This is a symbol for copper sulfate solution used at the start. You could also say, although they haven't mentioned it, concentration of copper sulfate solution. You want to make sure that you're using the same concentration. And you can also say surface area of metal used. So let's say all the time in the diagram, let's say metal powder. It looks like a powder, it's a pile, so it's not in pieces. So I would say use the powder version, not pieces of granules. The student repeated the experiment with metal Y. Table 1 shows 4 results for metal Y. Change in temperatures 9.2, 7.3, 9.5 and 9.2. Just by looking at this, test 2, the temperature change is quite different, at least 2 degrees Celsius different from the other test, which looks like an anomaly. That means if we are actually calculating the mean temperature, the question is, do we actually use this 7.3? Now it is best that we don't actually use it, because this is an anomaly definitely. So how do I spell anomaly? One second. That's no double Y. Anomaly, or you can call it the anomalous results, which mean you wouldn't be using this to find the mean. So let's ignore that. The marking scheme does say 1 mark. If you do use it, your average will actually go be different to the one that we are going to calculate. So how do we calculate this value? 9.2 plus 9.5 plus 9.2 again, divide that by 3, add them all up, which should give you 27.9 divided by 3 should give you 9.3 degrees Celsius. 9.3. If you did use the 7.3, you would wind up with 8.8 degrees Celsius, and you'll only get 1 mark instead of the 2 marks that you are being offered here. The more reactive the metal added to copper sulfate solution, the greater the temperature change. Figure 3 shows the reactivity series. Okay, so potassium is the most reactive, silver is the least reactive according to this list. Now, this copper sulfate, this reaction is actually called a displacement reaction. Reason being, here's copper. If you add silver to copper sulfate, silver is less reactive, so there won't be any reaction. But if you add zinc, magnesium, calcium, or potassium, all of them in powdered form, they will all react. And potassium will react the most. It will simply push away the copper or displace the copper and link up or bond with the sulfate to form the potassium sulfate salt, and copper will be displaced. So all 4 of these metals can displace the copper. Because they are more reactive. The student repeated the experiment. The student added magnesium to copper sulfate solution, which is more reactive than copper, an unknown metal A to copper sulfate solution. So these are 2 different experiments. They're not actually adding all of them together. So result 2, table 2 shows the results. With magnesium, the temperature change was 12 degrees. Metal A, it only changed by 8 degrees, which indicates metal A is less reactive than magnesium. If it was more reactive, then the temperature change would be higher. So the only metal that looks like that they've reacted is zinc here, because that's below magnesium. So use figure 3 and table 2. The student concludes that metal A is zinc. Give one reason why the student is correct. Use figure table. Since magnesium is less, no, not magnesium, zinc. Zinc is less reactive than magnesium. Now here they are asking you to give a reason. They are not asking you to give an explanation, but we can give an explanation. So it releases less energy, or you could say it is less exothermic as well, if they did ask for the explanation. You could also say, zinc is lower than magnesium in the reactivity series as well. You'll still get the mark. Or you could say the temperature change is less than magnesium with metal A. The student did the experiment with silver and copper sulfate solution. What happens to the temperature of the mixture? Now remember, silver is less reactive than copper. It's below copper in the reactivity series. Like I said at the start, in this here, silver is below copper, which means there won't be any reaction, so the temperature will stay the same. Okay? No reaction. suggest one reason why the student should not add potassium metal to copper sulfate solution. Now, potassium is the most reactive in the series. If you did add potassium with magnesium, it is actually increasing the temperature by 12 degrees. And potassium is above calcium as well. So the temperature increase is going to be way higher. In fact, potassium will react just with water in an explosive manner. So you wouldn't want to add it to copper sulfate, which releases more energy, right? So it is too dangerous. Right? Or you could say it's too reactive. Right? 100 centimeter cube of the copper sulfate solution contains 1.4 gram of copper sulfate. So here it actually links to the topic on quantitative chemistry, which is topic 3. Calculate the mass of copper sulfate in 25 centimeter cube of this copper sulfate solution. So if 100 centimeter cube contains 1.8 grams, what is the mass of copper sulfate in 25 centimeter cube? Right? Now, in 100 centimeter cube, you will have 4 25 centimeter cubes. And I'm trying to explain it while I'm trying to do this, which is actually the incorrect way. Let me redo it. Right? Right. Let me start again. So if I divide 25 divided by, actually, let me do it the other way around. I have got 1.8 grams in 100 centimeter cube. So if I divide that by 100, I would get the number of grams in 1 centimeter cube. And then all I have to do is multiply it by 25 to find the number of grams in 25 centimeter cube, which I should get 0.45 grams. Or let me do, not sure if I'm complicating this, but because it's for foundation tier students, it might be worthwhile to spend a little bit of time. So let's say these 4 boxes altogether is 100 centimeter cube. I've got 4 25s in there. 4 25 centimeter cube will add up to 100 centimeter cube, isn't it? So it's, if I want to work out the mass in just 125 of it, because in all 4 of them I've got 1.8 grams. So 1.8 divided by 4 will give you 0.45. There's another way of looking at it, 0.45. That brings us to the end of question 2. Let's have a look at question number 3, which is on the topic of atomic structure and the periodic table. This question is about gold and the compounds of gold. In the alpha particle scattering experiment, alpha particles are fired at gold foil. Now, the alpha particle scattering experiment is also tested in the physics paper. It's a crossover topic, right? So if you usually do chemistry paper 1 before you do the physics paper 1. So if you have a question on the alpha particle scattering experiment, then you most likely, right, 99% sure, you will not find a similar question on the same topic in the physics paper. You will find questions on isotopes and half-lives and so on, but usually not on the alpha particle scattering experiment. Right, going back to the topic. Question: alpha particles are positively charged. Table 4, figure 4 shows the results. So you got the alpha particle beam, right? Alpha is it's the symbol, and it has a +2 charge. If it's going straight, it hits the gold foil, and then some of it bounces back. These are deflected. Most alpha particles are not deflected. Most, meaning 99% of it is not actually deflected. It just goes straight through, as if the gold foil didn't exist, right? That was the observation, right? And it's about less than about 0.99%, right, got deflected, and less than 0.01% bounced back. That was the observation. So some particles were deflected. Complete the sentence. Some alpha particles are deflected because the nucleus of the atom is also positively charged. If alpha particles are positively charged, the nucleus should also be positively charged, because positive charges don't want to be near each other, they repel. Why are most alpha particles not deflected? The atom is a tiny sphere that cannot be divided. Doesn't explain. The atom is mainly empty space. That's the reason. The electrons orbit the nucleus at specific distances. Again, it doesn't give a reason for that. What was one conclusion? What was one conclusion from the alpha particle scattering experiment? The mass is concentrated at the center of the atom. Yes, right? Remember, the alpha particle experiment basically suggested, right, that the nucleus is in the center. It has a positive charge. It's mostly empty space. It didn't actually say that the electrons are in shells as well, right? Now the mass is spread evenly throughout the atom. That's actually the plum pudding model. Where you got the atom and the atom, or the entire thing, is positively charged, and you got electrons embedded in that, right? So gold reacts with the elements in group 7 of the periodic table. What are group 7 elements known as? These are halogens. Alkali metals are group 2 metals. Noble gases are group 0 or 8. Fluorine, chlorine, and bromine react with gold. Which element will be the most reactive with gold? Now, if you look at group 7 elements, you got fluorine, chlorine, bromine, iodine, astatine, and so on. Here, fluorine is the most reactive. And as you go down, reactivity decreases. It becomes less and less reactive. So it will be most reactive with gold is fluorine. Again, there's another question linking to topic 3 on quantitative chemistry. Any calculation is to do with quantitative chemistry. So is 3.7. So 34.9 grams of gold reacts with chlorine to produce 6.07 grams of gold chloride. The word equation is gold plus chlorine gives you gold chloride. Calculate the mass of chlorine that reacts with 3.94 grams of gold. Now, these are the reactants, and this is the product. Now, law of conservation of mass. Law of conservation of mass. What does that tell you? Total mass of reactants should be equal to the total mass of the products. So if you are reacting 3.94 grams of gold with chlorine, let's put it as X, and you wind up with 6.07 grams of gold chloride, then the additional mass came from chlorine. So all you have to do is 6.07 minus 3.94 will give you 2.13 grams. 2.13. Calculate the relative formula mass of gold chloride. You got AuCl3. So this small 3 basically means you got 1 atom of gold and 3 atoms of chlorine altogether. So they want the total mass of the entire thing, and they've given you the mass of chlorine is 35.5, gold is 197. So that's 197 plus 35.5. Let's multiply it by 3 rather than writing it 3 times. That should give me 197 plus, if I do the multiplication first, that's 106.5. Add them up again, that should give you 303.5. 303.5. Now, do I write grams here because they're asking for relative formula mass? Relative formula mass actually doesn't have a unit, right? Although we commonly put grams as a unit. Question number 4 is on the topic of atomic structure and the periodic table again. This question is about elements and compounds. Figure 5 shows the proportion of elements in the periodic table that are metals and non-metals. Metals is the most of the in the pie chart. The non-metal is only 2 divisions. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So metals is 8 out of 10, which is 0.8 or 80% of it is metal. And non-metal is 2 out of 10, that's 1 over 5, that is 0.2, which is 20% of it is metal. Determine the percentage of the metal of the elements in figure 5 that are metals. Right? We just worked it out to be 80%. Right? So it's 8 over 10 times 100. Give you 80%. Give 2 physical properties of metal. Now that's a long list, isn't it? Right, let's list as much as possible. So metals conduct electricity. They conduct thermal energy or heat, right? Conducts heat. They are ductile, meaning that it can be drawn into wires, similar to chewing gum. So if you pull it, it becomes really thin and more like a string. Have high melting point. I'm writing it as MP, but make sure that you write it as melting point in 2 words. Or you could say have high boiling point as well. Again, write it as words rather than BP. Otherwise, they'll think it's blood pressure. You could also list, let me write some additional this thing. Are malleable. Meaning that they can be hammered into shapes. Are shiny. And are strong. Right? But any of the first four is actually the best properties, because some metals doesn't appear as shiny, right? Some metals are not as strong. For example, potassium and sodium, you can cut it with a butter knife, so they're not actually that strong, are they? So sodium reacts with chlorine to produce sodium chloride. Balance the equation. So you've got one atom of sodium, one atom of sodium. There's two atoms of chlorine, so you have to add here. So you multiply the entire thing by 2, which makes sodium, there's 2 now. So you add, balance the sodium. Figure 6 shows part of the structure of sodium chloride. Now sodium chloride, remember, is an ionic compound because it's made up of sodium is the metal, chlorine is the non-metal, right? And it's this Cl minus is the chlorine, and the Na plus is the plus is the positive charge is the sodium. So the positive charge is the Na plus ion, and the minus ion is the chloride ion. And what you're seeing is actually a giant lattice structure, right? Right. What holds the particles together in sodium chloride? That would be electrostatic attractions between the positive and negative ions. Let me get rid of that. Intermolecular forces, right? They usually be between covalent molecules. Metallic bonds, that's between metals. Solid sodium chloride does not conduct electricity. Give 2 ways in which sodium chloride can be made to conduct electricity. Now, if you want it to conduct electricity, it needs to have, right, charged particles, which are ions, right? Ions of the sodium ions and the Cl chloride ions should be mobile, meaning that it should be able to move. So how can you get it to move? Well, you could dissolve it in water. Sodium chloride is a salt, so it will dissolve, it will separate out when it dissolved in water to form salt water, right? Dissolve the, again I'm writing the chemical formula for sodium chloride, NaCl, in water. The other thing that you can do is heat the sodium chloride until it is molten, or until it becomes a liquid, right? You can see heat sodium chloride, and the temperature is about 1500 degrees Celsius. At that, it's really high, and at that temperature the sodium chloride will dissolve in turn to liquid. Question number 5. This question is about elements in the periodic table. Again, so it's on topic 1. Topic 1 is actually a big topic, and topic 2 on bonding is also quite big. What properties are used to arrange elements in the early periodic table? The early periodic table was arranged according to the atomic weight, right? Atomic number is the modern periodic table. Actually, although we say atomic number, it is actually based on the proton number. If you look in the periodic table, the bottom number, for example, carbon 6 and 12, that 6 is the atomic number or the proton number. In early periodic tables, iodine was placed before tellurium. Mendeleev placed iodine after tellurium. Figure 7 shows part of Mendeleev's table. So this is iodine here, I, and tellurium is to the left of it. So in early periodic table, iodine was placed before. So it was in the early periodic table. Let me write. In the early periodic table, it was I and then Te. The Mendeleev's is actually Te and then I. Suggest one reason why Mendeleev placed iodine in the column shown in figure 7. Why did he swap it around, right? Did he actually know the proton number or the mass number? It's very close to each other, right? And doubted he was able to actually measure up to that much. But what he did know was the pattern, right? Mendeleev basically figured out that all the elements, right? This is group 6 and this is group 7. Mendeleev figured out all the elements in a group shared certain properties, or rather than shared, had similar chemical properties, right? Meaning that, for example, in group 1, they all react with water, right? Fluorine also reacts with, they all react with metals as well in different ways. Meaning fluorine can react really strongly than bromine, but tellurium doesn't actually fit that pattern. So that's why he actually swapped it, because fluorine, chlorine, bromine, and iodine, they all react in a similar way to each other, right? So reason being that he actually moved it was because iodine had similar properties to fluorine, chlorine, and bromine. Table 3 shows the melting points of 3 group 1 metals. You got lithium, sodium, potassium. This is actually the group 1. This lithium is on the top. Potassium is actually towards the bottom, the third element in that group. So what is happening to the melting point is actually going down. What state is lithium at 100 degrees Celsius? Now, at 100 degrees Celsius, right, it would be a solid because it takes 180 degrees for it to melt. Complete the graph in figure 8. Use table 3. You should complete the scale on the y-axis. Draw bars to show the melting points of sodium and potassium. Right, sodium is 98, potassium is 63. 98 and 63. So 98, 63, that's sodium and potassium. We need to label the, which axis are they asking? Complete the scale on the y-axis. Okay, so they've gone up to 100. So we need to go up to maximum of lithium is 180. So they have drawn the bar for lithium and they're going up in tens. So 110, 120, 130, 140, 150, 160, 170, 180. Do you need to write all of them? You could skip one after each other, right? As long as you've written about 3 or 4 of them, it's fine. So this goes up to 180. Sodium needs to go up to 98. So I want to draw a bar which is the same width, that's 8 boxes. So I want to start, the width of the box should be from there to there, between that 98. You got 90 here, and then each box is 2, so it needs to go right up to there. So let me draw a flat line. And then draw a straight line down. So that's sodium, 98 degrees. Let's use a different color for potassium. Potassium is 63. So as you can see at the bottom, potassium is 63. So I want to start the bar here, and it should be that thickness, 63. So that's 60, 62, and then halfway point. Right? So you need to make sure that you actually are drawing this straight line. We can get that straight. Halfway, and then straight down. Slightly gone side, isn't it? Slightly thicker than what I want. There you go. And that's potassium at 63 degrees. You don't have to write the value. I'm just writing it so that you can see the values here. Question number 5.5. Lithium reacts with chlorine to produce lithium chloride. Figure 9 shows what happens to the electrons in the outer shell when a lithium atom reacts with a chlorine atom. The dot and crosses represent the electrons. So lithium is the metal here. It's a group 1 metal. Chlorine is the non-metal, and that's in group 7. Now, being a metal, lithium loses 1 electron. It's this electron that is actually losing it. It is actually losing it to the chlorine, right? So chlorine gains 1 electron. Why is it doing it? By losing that electron. So lithium is the third element, so it has 2 and 1 electron. That's the electron configuration or electronic structure. So by losing that electron, it will have 2 electrons in its one cell. It becomes more stable. Chlorine, by gaining that electron, it starts off as, it has 17 electrons, so 2, 8, 7, and it's trying to fill that last shell. And what you have is lithium ion and chlorine ion, right? Because of the positive and the negative charges. Describe what happens to the lithium atom and to a chlorine atom when they react. So they start off as atoms here, right? On this side, these two are atoms. These two are ions. So the atoms change into an ion, right? Both of them change into ion. So use figure 9 to answer in terms of electrons. So ions are formed, right? So you could say lithium forms positive ions or ion. Chlorine forms negative ions, right? Why are they doing it? Here you can see in the lithium, it doesn't have any electrons in the second shell, whereas chlorine has a full set of 8 electrons in the third shell, right? So they both have a full you could say stable outer shell or energy level, right? Oh, I missed one bit, the third one. We forgot to mention the loss of electrons, because you need to talk in terms of electrons. So I would write this as my first point. Lithium loses 1 electron, chlorine gains 1 electron. You need to say both of this to get a mark, right? And these 3 points are another mark, and this is the third mark. Five 5.6, lithium and potassium are in the same group as the periodic table. Figure 10 represents the electronic structures of lithium atom and of a potassium atom. As I said, lithium has 3 electrons. If you look in the periodic table, this is what you'll see. Proton number is 3, mass is 7. So it has 3 electrons, 2 in the first shell, the third in the second shell. So 2, 1 is the electronic structure. Potassium is the 19th element, okay, 19, and the mass I think is 39. I won't double check that, but we are more worried about this number of electrons, 2881, making it 19 electrons in this 4 energy levels of 4 shells. So if you count the crosses, you'll find 2, 8, 8, and then 1 in the last shell. Give 2 reasons why potassium is more reactive than lithium. Right? Now, how these 2 atoms actually react is by losing the electron in the last shell. So lithium tries to loses that electron to become reactive. Potassium is losing that electron in the last shell. Right? So whichever atom loses this electron easily is more reactive, right? Now you think that lithium has only 3, so we'll make it easy. Actually, this electron is actually attracted towards the nucleus, because remember, the nucleus is positively charged, electrons are negatively charged. In potassium, the positive charged nucleus is much further away from this electron, so it's not attracted that much, which means this electron can easily wander off and escape somewhere else, and potassium manages to lose it. So give 2 reasons why potassium is more reactive than lithium. You could say, remember, going back to the Group 1, lithium, sodium, potassium, not calcium, right? Lithium, sodium, potassium, rubidium, I think. Right, anyway, this is group 1, right? So reactivity decreases down the group, right? Now they would actually accept this answer. They're not asking you to explain why. Give 2 reasons. You could also, I'm going to use a different color, right? Potassium has more shells or energy levels, right? Or you could say potassium, let me use the symbol. Potassium can lose or its outer shell electron more easily. You could also say potassium has an outer shell further away from the nucleus and you can also say potassium has more shielding, meaning the other shells actually shields the attraction between the nucleus and this outer electron. Finally, you could also say potassium has a weaker attraction between nucleus and the outer shell electron. Any of these, that's 1, 2, 3, 4, 5, 6, 7 different points. Any of them will be fine to get you any 2 of them will get you the 2 marks. That brings us to the end of question number 5. Question number 6, as I said, is actually the higher paper question number 1, which is on the atomic structure again. It links to the chemical changes topic as well on electrolysis. And question 7 is question 2 in the higher paper, which links to bonding and properties of matter. And question 8 links to the quantitative chemistry. It's actually again a practical thermal decomposition of metal carbonates. It links to quantitative chemistry and chemical changes as well. But here's the 6-mark question in there, so which is question 3 in the higher paper. So for what I will do is I will do the videos for those questions separately for the higher tier paper and attach it to the playlist for this video, so that you should be able to watch those videos and answer these questions if you're revising. Thanks for watching. This is Katish here. If you like the video, give us a thumbs up, comment on any questions, and I don't know, subscribe if you think this is useful. Thanks for watching.